My name is Blake.
I'm Brian.
And I'm Clark. This is our automated drink mixer. So our project uses a HMI touchscreen to mix drinks and create different combinations for our drinks. We use an ESP board to run the entire thing, and in the end we have a fully automated drink dispenser with 6 customizable powder slots. What we originally planned was to have 8 different powdered slots with level sensors for the powder, but due to size constraints and budget constraints, we were not able to make that happen. We also planned to have RFID sensors, but those were never delivered.
So in order to actually turn this project into an actually functional thing, we needed to plan out the hardware that we would use. So the first thing is our board, which is our HMI. This is how we use to interface our drink mixer into our hands. So it'll have all the buttons to customize your drink. The second is our controller, which we mentioned before, which was our ESP32 board, which was a cheap and small way to power it without having to spend a couple $100s on a PLC. Next, that thing that we did not include was RFID sensors, which was going to automate our drink mixing sequences. So if you wanted to customize a certain drink, we intended to have an RFID sensor that you can scan. The next is the sensors for powder slots. So we also intentionally wanted to have it to where if we ran out of powder, we would have a notification that would pop up and then it would tell, hey, the powder is run out. But again, we did not get to that part. The next part is our H-bridge. So this is how we use to control our linear actuator. Because we needed both up and down motion, we couldn't just use what we used as a MOSFET, which would control one motion. So the H-bridge basically allowed us to move the linear actuator up and down. Diodes were to prevent backflow current. So in case we wanted signals that didn't want to go a certain way or feedback to the ESP, for example, and damage the board, it would prevent that backflow of current. Next, we had the 6 powder slots, which would allow us to customize 48 different drinks in different combinations. So if you have powder slot 1 or 1 and 2, you can have a bunch of different drinks. And then the last is our organization. So you can have terminal blocks that we used, and then we put all of the wires and wiring into the back of our drink mixer to kind of compile it and have it somewhere neat.
The automated drink sequence, it starts off with the user selecting the slots. There's up to 6 slots that you can select. Once you hit create drink, it will send a Bluetooth signal to the actual drink mixer, and it will start dispensing powder, water, and it'll start raising up the cup. And once it does that, once the linear actuator reaches the top of its travel. There we go. It will start mixing it'll start mixing it with the mixer that we have, and then once that is finished, it will lower down and it will let you grab the drink. The RFID drink mixer preset system plan that we had before it wasn't delivered was we were going to make it to where you could make a drink, and while the drink was being made, you could tap the RFID sensor card onto anywhere that had an RFID sensor, and it would write the system's data to the card. So anytime you wanted to make a drink, you could just tap it on and it'll start making the drink for you. The BLE communication system. BLE stands for Bluetooth Low Energy, which is really good, so we don't have to use too much energy. It starts off, whenever you power on the machine, it will advertise its Bluetooth signal to the machine. So the ESP32 can read it, and then it can start sending out signals to each other. And once a drink is made, the screen will send out a signal with a bit mask to the ESP32, and the ESP32 will take that bit mask and will separate out to each of the different motors. And then, just in case if the power ever turns off, it will send a signal every 3 seconds to check to see if it's connected, and if it's not, it will start trying to reconnect automatically. There are 3 different Bluetooth systems that get sent out. The system to send out the the bit mask, there's the system for the RFID sensor, and for the sensors that we had to check to see if there was still powder in there.
So I'm going to take you through all of our design process. So this was the beginning stages. So one of the first things that we bought was an actual handheld mixer, which I deconstructed and took out this part that you see right here. And the way that I adapted it to fit into our mixer was kind of creating a shell that would eventually go into the part that would actually mix the drink. The next part, which was arguably the most important, was the powder dispensing system. So what we use is an auger-based system that would basically push out powder and kind of move it in a way to bring it to the drink. So if you see here, this is where the slots would be for our powder slots, and then the auger would be exposed right here, which the powder would fall into, push forward, and then drop underneath it, which would be a little bit more forward. And then here is a first kind of like general assembly of our part. So you can see here it wasn't exactly finished, but over time as we progressed, we were able to kind of build on and add parts until it came to the part that we have today. And then here's a couple of our first like major prints. So this big part kind of took up the entire build volume of our plate. And then here we have the linear actuator, how we connected that to have the platform where we would raise the cup into the mixer. And then here is like the very bottom of the base with that linear actuator, kind of just showing how we incorporated the parts and how they were all assembled. And then here is the final like full assembly of like an actual printed. So you can see here that we have the part, mixer, and then we have the motors actually attached with the augers, and then linear actuator of course, and then of course you can always add the cup later on. And then from the CAD design we have like a little engineering sketch of it right here, and then here's the real life model.
This is our wiring diagram that we use. It shows all of our components, and on the motors it shows which powder slot it goes to and how much voltage it uses.
Some challenges that we faced, the first main challenge was it kept on getting stuck in a boot loop. What that means is it would keep on restarting over and over again, and you wouldn't be able to do anything with the screen. It just stayed with its backlight on. Another one, whenever we fixed that, there was a problem with the PS RAM. We didn't have PS RAM enabled, and we were trying to fit all of the screen's information into its main code area, which did not work. So we had to enable a PS RAM, which is a setting with the screen. The next problem that we had was the Bluetooth could not find each other. We had to use a different Bluetooth library that was meant for ESPs. And the wrong core version, we were trying to use the most recent core versions for the ESP32s, but they did not work with the program that we used to make the screen. So we had to put it to an older version that supported. And one of our less bad problems was the mixer delay was too long. It was 22 seconds, and it needed to be shorter so that way it could raise up to the very top of its travel, and then it would start mixing it, and then it would start going down once the mixing is finished.
So this video, you can get it when
You should just be able to click it towards the computer.
This video shows us during our early testing phases, testing how long the drink mixer runs for. And at the end of the video, you see how there was still powder left at the bottom. So the drink wasn't quite ready. We needed to extend the mixer timer. That's me on there, and there's powder left at the bottom.
All right, this is the screen. This is when it was just finished, and it's showing how it works in action. It is me selecting the slots, and it is sending over all the information to the other ESP, which is connected to the computer, and it's showing it turning on all the powder slots, the mixer, the delays, and the linear actuator. So go faster.
This is one of our last tests during our testing phase. This shows one of the problems we had in our code. The water pump pumped for too long. It was on when it wasn't supposed to be on, and it made a mess, as you can see in the video. I'll let that play out.
So one of the ways that we had to fix that was we discovered that the code wasn't actually supposed to do, or wasn't actually doing what it was supposed to be doing, and as a result, it ended up kind of making a big flooding mess that we didn't exactly like.
We had the code in there to where it was easy to change the timing, but the code that was actually running wasn't using that timer.
This is our completed project. On to the demonstration.
Any questions for the demonstration?
I have a question. Given more time and a larger budget, what would you have done differently?
I think one of the main things we could have done is had a faster linear actuator. If we had a faster linear actuator, I think it would have been able to mix better because it could have mixed while the powder was dispensing and our water was dispensing. We probably could have reordered the RFID sensors, so we could have had that included. And we might have been able to also include the sensors for to detect if the powder was empty or not for specific slots.
Another thing that we talked about early on was organization of wires. So in the beginning, we wanted to have a custom PCB built for this machine, which instead of having like a bunch of wires and terminal blocks, it would just be able to be like a plug and play for wiring. So you would literally be able to just take your motors, kind of just have them exactly to the custom PCB board, and it would make wiring and everything a whole lot easier and nicer.
I have a question. I have two actually. So with this project, what's your target audience? And with that, how would you go about cleaning it? Because it seems like cross contamination could be a problem with this.
Your first question was, say again?
Target audience.
Target audience. Anyone that likes to have different drinks and they are too busy to mix it, to portion it out and mix it themselves. So anyone who wants protein shakes, anyone who wants Kool-Aid, anyone who wants lemonade, they can just have that hooked up to their device and have it run so that they can just grab it and go. To clean it, this is a prototype and we aren't able to have injected molded plastic, so it's just 3D printed right now, which is hard to clean. But we would use food safe materials in our actual product.
Ideally, you'd be able to break it down and have, like, you would be able to wash your parts and make sure that in between uses or however long you decide you want to wash it, you'd be able to clean it.
So this is for retail, not mass production?
With this version, it's kind of expensive, but we are planning on attempting to make a less expensive version that could be used in everyday homes that everyone could use.
When it comes to the powder dispenser, what made you decide to use the time-based system versus weight-based?
Using a weight-based system would be a lot more expensive and it would be harder to code than timing.
You can actually get pretty accurate results with an auger and timing because it's relatively the same rotation and speed.
Based on your design, what safety measures have you developed, since there are augers and there's multiple ways to get in there and hurt yourself? Did you think about any safety parameters, or is that just something you haven't reached yet?
That isn't something we've reached yet. We've discussed adding lids for the powder containers, but that is for a later time.
All right, here's our demo.
It is 1 and 6.
Here we have our very own Arnold Palmer. Delish.
How the drink presets work, it saves the slots that we just used. Okay.
Here we have another Arnold Palmer. Delish.